The cosmos we once imagined no longer exists. For all of human history, we looked up and saw the same thing: an endless, calm void. A passive, unchanging backdrop to our lives. But that was just a habit, and it no longer matches physical reality. The space around Earth has stopped being empty. Over the past 60 years, we've transformed it into a dense, dynamic environment. It's no longer just a background, it's a system. Every new object we launch changes everything else. Orbit is a place that collects the consequences of our actions, and this buildup is slowly yet irreversibly reshaping the entire system. How did we end up realizing that the vastest space imaginable could actually feel cramped? How can an ordinary coin orbiting Earth turn into something like a bomb? And what exactly is the tipping point when space starts tearing itself apart, triggering a chain reaction? That's what we're going to explore. This isn't just a concern for engineers and astronauts. Our modern civilization relies critically on satellites. They power the navigation systems in airplanes, trucks, and your smartphone. They keep financial transactions synchronized, manage power grids, and help forecast the weather. In fact, the list goes on and on. Nearly every complex system, from maritime shipping to telecommunications, depends on this invisible infrastructure floating overhead. Losing it wouldn't cause an instant collapse like in the movies. Instead, it would trigger a cascade of failures. First, navigation errors, then communication delays, followed by breakdowns in logistics. A slow, systemic unraveling of everything we depend on. So, if space is no longer empty, and our lives depend on it, what exactly fills it? The answer moves at 8 kilometers per second, and it doesn't forgive mistakes. So what exactly fills the space we usually think of as empty? The answer is our own past. Over more than 60 years of exploring space, we've left behind more than just functioning machines. We've abandoned rocket stages, discarded nose cones, tools dropped by astronauts, bolts, nuts, even flakes of paint. And of course, fragments from both accidental and deliberate explosions. Earth-based tracking systems constantly monitor tens of thousands of objects larger than a smartphone. But that's just the tip of the iceberg. Hundreds of thousands of smaller fragments, about the size of a coin, have already slipped below detection limits. And millions of tiny particles, capable of piercing a spacesuit, are impossible to catalog. They simply exist. Everything up there, satellites and debris alike, moves at an astonishing speed. About 5 miles per second. That's 10 times faster than a bullet fired from a rifle. At this velocity, the physics we take for granted on Earth start to change. A collision isn't just a hit. Imagine a simple coin. In your pocket, it's harmless. But hurl it at orbital speed, and its kinetic energy matches that of an explosive device. When it strikes, that energy releases instantly. It's not a collision. It's an explosion. The coin vaporizes, along with part of the target, turning both into a fiery cloud of plasma and thousands of tiny fragments. Each fragment becomes a new bullet. The threat doesn't disappear, it multiplies. The idea that space might start generating its own threats isn't new. Back in 1978, a NASA astrophysicist named Donald Kessler published a paper that sounded like science fiction at the time. He calculated that if the density of objects in low Earth orbit reached a certain critical point, a chain reaction would kick off. Collisions would create debris faster than it could burn up in the atmosphere. Each crash would increase the chance of the next one. For decades, this theory remained just a hypothesis. Launches were infrequent, satellites were few, and space was vast enough for everyone. Then the economy shifted. Mega constellations of satellites like Starlink emerged. From a business standpoint, their strategy is flawless. Mass-produce satellites, launch them cheaply, and provide global internet coverage. This opens space to commercial opportunities like never before. But from a physics perspective, thousands of new satellites occupying the same orbits mean a dramatic increase in congestion. Low Earth orbit isn't an endless ocean. It's more like a network of narrow, overcrowded highways. The more vehicles on those roads, the greater the chance of collisions. The orbit stopped forgiving mistakes. It now demands constant vigilance. active coordination, and the processing of massive amounts of data.
Here's proof that the system is already pushed to its limits.
In just one recent 6-month stretch, Starlink satellites performed more than 25,000 collision avoidance maneuvers. 25,000 times, either automated controls or ground operators changed a satellite's course to prevent disaster. That number alone is staggering. But what's truly alarming is this. It's more than double the figure from the previous 6 months. The increase isn't gradual, it's exponential. Since Starlink started operating in 2019, the total number of such maneuvers has topped 50,000. To be precise, by the time this video was recorded, the count was even higher, and still accelerating. Forecasts predict that by the end of the decade, this single satellite constellation will need to execute hundreds of thousands of evasive maneuvers every 6 months. And that doesn't even include similar projects from other companies and countries already on the horizon.
But those are just numbers. What really matters is what happens when there's no maneuver. On February 10, 2009, nearly 800 kilometers above Siberia, 2 objects collided. One was an active commercial communications satellite, the 33rd Iridium, weighing 600 kilograms. The other was a decommissioned Soviet military satellite, Cosmos 2251, weighing almost a ton. They crashed into each other at a staggering speed of 11.7 kilometers per second. No one saw it coming. Tracking systems didn't issue any warnings. In an instant, 2 intact satellites shattered into a cloud of thousands of trackable fragments, and countless smaller pieces that went unnoticed. This marked the first ever collision between 2 artificial satellites in history. These fragments haven't gone anywhere. They're still up there, orbiting Earth. At such a high altitude, the atmosphere is so thin that debris can take decades, even centuries, to naturally fall out of orbit. The cloud of fragments from that single collision stretched out, polluting an entire layer of orbital space. Even now, more than 10 years later, satellite operators have to maneuver regularly to avoid pieces from Iridium and Cosmos. One accident created thousands of long-lasting hazards. But what happens when the debris density grows so high that these hazards start causing their own collisions? What if this process becomes self-sustaining, sparking a chain reaction, even if we never launch another satellite again? This phenomenon has a name, the Kessler Syndrome. It's not science fiction. It's a physical model developed by NASA scientist Donald Kessler back in 1978. He calculated that once objects in orbit reach a certain density, collisions will generate debris faster than the atmosphere can burn it up. And at some point, this process becomes self-sustaining. Wait, let me say that again. Self-sustaining. That means it keeps going even if we stop launching anything into space entirely. Forever. Orbit would start to consume itself, and we would have no way to stop it. This isn't just some theoretical point far off in the future. We can already see the system feeding itself. Every active satellite will eventually turn into debris. It has to keep performing avoidance maneuvers, burning through precious fuel. Once that fuel runs out, the satellite loses control. Without fuel, it becomes a passive object, unable to dodge collisions. Tons of metal, just waiting for their moment to join a growing cloud of fragments. The result of the Kessler Syndrome will be that the orbits we rely on most will become nearly unusable. Not just dangerous, but economically pointless. Sending satellites into those orbits, each costing hundreds of millions of dollars, will be like parking a brand new sports car in the middle of an artillery barrage. We are building an impenetrable wall of debris around the planet with our own hands. It would be bad enough if this debris field grew only from accidental collisions. But we keep pouring fuel on the fire, intentionally. I'm talking about tests of anti-satellite weapons. Here's how it works. A country wants to showcase its military strength, so it launches an interceptor missile at one of its own aging satellites. The missile hits its target. What was once a single controlled object explodes into thousands of uncontrollable fragments. The news frames this as a technological victory. In reality, it's an act of global vandalism. These fragments don't stay over the country that conducted the test. They ignore political borders. The laws of physics send them scattering along global orbital paths, turning them into hazards for every satellite at that altitude. American, European, Chinese, private. Every satellite. And these dangers last for years, actually decades. On higher orbits, even centuries. A single so-called successful launch can contaminate an entire layer of space for a whole generation. So, what are we doing to stop this? Solutions exist, on paper. There are international guidelines requiring satellites to be deorbited within 25 years after their mission ends. Technologies for active debris removal are in development. Cleanup satellites equipped with nets, harpoons, robotic arms. It all sounds promising. You get the sense the problem is under control. But that's an illusion. Here's why. Almost all these measures rely on voluntary compliance. They are guidelines, not laws. No international authority exists to force a country or company to clean up after itself. Cleaning up space debris costs a fortune, and nobody wants to foot the bill. Legal frameworks that define responsibility for creating debris remain vague and incomplete. The result? Everyone recognizes the danger, but hopes someone else will handle the cleanup. The problem is no longer political, it's mathematical. The number of objects in orbit grows faster than our ability to track them, let alone remove them. With every new launch, every collision, every weapons test, the margin for action shrinks. Satellite operators find themselves trapped. Make an extra maneuver, and they burn precious fuel, shortening the satellite's lifespan. Skip the maneuver, and they risk losing everything. We found ourselves trapped in a mathematical snare of our own making. A trap governed solely by the laws of physics, not by our good intentions. And every day, its walls tighten, squeezing in closer and closer. The question is no longer if it will snap shut. The real question is when, and what exactly will come crashing down on us here on Earth. We've been asking the wrong question all along. We wondered when a satellite would break, or when two fragments would collide. But that's like asking which single raindrop will cause a flood. The rising number of avoidance maneuvers isn't just a series of isolated events. It's a symptom, a warning sign of systemic stress. The whole system is under pressure, and it's starting to crack at the seams. To understand what's really happening, we need to stop talking about space debris. That term misleads us. It makes us picture a distant junkyard, something far away and unimportant. But what we've created above us is humanity's first large-scale environmental crisis beyond Earth's atmosphere. It's not a dump. It's more like an oil spill coating the entire planet, like cutting down a forest that will never grow back. We treated orbit like an endless ocean, a place where we could dump waste, and it would just take it. It turns out, it can't. Here lies the key difference. When we pollute the ocean, it fights back. Microorganisms break down oil. Currents dilute toxins. Life, slowly, over decades, reclaims its ground. Forests regrow after fires. But low Earth orbit has none of these healing powers. No biology, no chemistry, no weather to cleanse itself. Every bolt, every drop of fuel, every fragment will remain there for centuries, governed only by the laws of ballistics. Orbit does not heal itself. Never. This changes everything. Thinking of orbit as an endless frontier, like the Wild West where anyone can stake a claim, that mindset belongs to the 20th century. Today, orbit is critical infrastructure. Like bridges, power grids, or internet cables beneath the ocean. It has a finite capacity, physical limits, and we have reached those limits. Here's the verdict, based on mathematical models. If the current pace of satellite launches keeps up without serious cleanup efforts, access to low Earth orbit will shrink dramatically within a single generation. To be clear, not could shrink, but it will. This isn't a forecast anymore, it's a calculation. And the cause won't be a war in space or a technology failure. The cause will be us. Our own accumulated debris will block the way upward. This map shows more than just navigators and satellite internet. The road to the moon, to Mars, to deep space, every journey to the stars begins right here, just a few hundred miles above our heads. This thin layer of space forms our only gateway to the universe, and right now, we're clogging that gateway with debris. How easily we pass through depends on choices we make, or fail to make, in the coming decade. We don't have centuries. We don't even have 50 years. We have about 10 years to change course. Orbital space won't forgive us. It won't heal on its own. It will simply respond according to the laws of physics. And for the first time in history, humanity faces a problem that no single half of the planet can solve alone. This is our shared home, and our first collective test of maturity beyond Earth.